Day Bayaw, welcome back to our YouTube channel Bayaw Tutorial. In this video, we are going to solve a problem from thermodynamics and heat transfer that involves the chapter 7 refrigeration system. So here is our problem. A steady flow Carnot refrigeration cycle use R-134A as working fluid. The refrigerant changes from saturated vapor to saturated liquid at 60 degrees Celsius in the condenser as it rejected heat. The evaporator pressure is 140 kilopascal. Determine the COP, the amount of heat absorbed from refrigerated space, and the net work input. So here in our problem, we are asked to determine the three unknowns: the coefficient of performance, the amount of heat absorbed from refrigerated space, and the network input. But before we are going to solve what is asked in this problem, we need to identify first the given values. So we have the temperature at condenser, or the maximum temperature is equals to 60 degrees Celsius, and our minimum pressure, which is equals to 140 kilopascal. So we have properties for this problem, and you can see the properties at table A-12. The saturation temperature at 140 kilopascal is equals to negative 18.77 degrees Celsius. The specific enthalpy of saturated vapor is equals to 239.16 kilojoules per kilogram. And at table A-11, the value for our specific enthalpy of saturated vapor at 60 degrees Celsius is equals to 278.46 kilojoules per kilogram, and the value for our specific enthalpy at saturated liquid at 60 degrees Celsius is equals to 139.36 kilojoules per kilogram. Now that we identified the given for this problem, we need to identify first the equivalent saturated temperature of evaporator. So A, the coefficient performance of the refrigeration cycle is equals to the minimum temperature divided by the difference of maximum temperature and the minimum temperature. So it is in terms of temperature. So by plugging the given values, we have negative 18.77 degrees Celsius plus 273 Kelvin divided by 63 degrees Celsius plus 273 Kelvin minus negative 18.77 degrees Celsius plus 273 Kelvin. And by equating this equation, we can now get the value for our coefficient of performance, which is equals to 3.2275. Next is we need to determine the amount of heat absorbed from refrigerated space. So we have the amount of heat absorbed is equals to the specific enthalpy of saturated vapor at 60 degrees Celsius minus the specific enthalpy of saturated liquid at 60 degrees Celsius. So we have 278.46 minus 139.36. We have 139.1 kilojoules per kilogram. Now that we have the value for our heat absorbed, we can now solve for the network input. But before that, we are going to find the heat rejected in the refrigerated space. So we have QH divided by QL is equals to TH divided by TL. And by equating this equation, we can now get the equation for our QL, which is equals to QH times TL divided by TH. So by plugging in the given values, we have 139.1 multiplied by negative 18.77 degrees Celsius plus 273 Kelvin divided by 60 degrees Celsius plus 273 Kelvin. It is equals to 106.1964 kilojoules per kilogram. So now that we have the value for our rejected heat and the absorbed heat, we can now solve for our network input. So the network input is equals to the difference of the heat absorbed and the heat rejected. So the value for our heat absorbed is equals to 139.1 kilojoules per kilogram, and for our heat rejected, it is equals to 106.1964 kilojoules per kilogram. So here is our equation. And by subtracting these two values, we can now get our network input, which is equals to 32.9036 kilojoules per kilogram. So the amount or the value for our COP is equals to 3.2275. The amount of heat absorbed from refrigerated space is equals to 139.1 kilojoules per kilogram, and the network input is equals to 32.9036 kilojoules per kilogram. So that's it. Here is the answers in this problem.